Hi, good evening. This is Navin Shrestha. Your USK ID number u1095456 is the 16th of December. Sorry, it's the 16th of October. I've been doing this assignment for too long. Sorry. From the top of the code, I've called it a self-aligning code. I might rename the title later on, but for the moment, it's alright. So from the top, I've started with including calling into the classes for the gyro, and after that I've got my PID constants over here. This has already been figured out, and this is configured to that 10 and 9.1. I didn't actually put integral constant because I as you can see with my rig setup, I don't actually have anything that would help me measure the tenth of the angle change that the integral actually corrects. So all I have is this straight edge of a book where I can actually compare my angle to the positions by the sign board or my prototype board. So I'll go with the physical side, physical components or the mechanical components of the board first. As you can see, the top the mechanical design is pretty easy over here. All the components pretty much lined up to the main axis of it, so that the motors don't have to thrust too much power onto it for rotating the sign board clockwise or counterclockwise. This is the rig that I've got set up over here. It just is held by a small keyring and a nylon wire. The board is pretty much a cover book cover. I've got a 9-volt battery on the top for charging the Arduino, and then I've got a motor shield, and underneath it I've got the Arduino Uno 328 Atmega board. Then I've got two micro motors with propeller hubs on them attached to them. At the side of the thing I've got two LED bulbs which I've attached to the Arduino board. These are pretty much for debugging process. So when my motor, one of them, starts up countering the spin of the board, then my relative LED light actually starts glowing up, and vice versa. At the top there's actually the gyro over there, and it's on the x-axis, so our code is actually built into read the x-axis of the gyro. At the back of this board I've got a 4 1.5 volt AA battery pack. So that's pretty much the physical or the mechanical side of the whole board. I've just got plus and minus on the board, because when it turns counterclockwise it's doing plus, and when it's doing clockwise it's doing minus angles on the position. Okay, let's go back to the code now. So from the top, as I said, there are the PID constants over here which I've configured. These are my test definitions. Later on, whenever I actually define one of them, I can straight on plug into my Arduino and then just define them, and then if I upload it to the Arduino, those certain test starts working. And then as I was explaining, I had two debugging LEDs. These are the two debugging LEDs, and later on I'll show you which one is actually respected to the whichever board. So the 10 is for motor A, and LED 2 is for motor 7 is for motor B. After that, I've got my unsigned longs for time variables, start time, differential time, time differential, end time, and the time interval. This time interval is pretty much for my tests A and B, because on the assignment questions I've been told to test them for 10 seconds, so they are pretty much doing just that. The float over here is actually to, later on I'll show you why the float TS is there. This pretty much gives the time difference in decimal points, because when we change the code actually only records milliseconds, but when we are taking the constants and trying to calculate the integral and differential values of them, we have to get them in seconds. So this comes in handy later on. After that, I've got my variables set up for my gyro readings, ZX, ZY, GZ, AX, AY, AZ, even though I'm not using all 6 of them. I'm only using the one ZY value, GX value of it. So everything below that is pretty much related to the x-axis of it, and I got a set point over here, and then a position value as well. I've just initialized them, most of them, into 0, because just in case there was any values not being shown on the variables, I didn't want the Arduino to go and get its own variable out of nowhere. So the first block of code over here is the function to read gyro. It's a pretty simple function. It just calls the function through the MPU class, 6050 class that was actually called on the top. And then it's just converting that raw GX value into the variable raw underscore x. Probably I'll just point it out here. I've got raw x as a float, because gx is an integer, 16-bit integer, but float, it has got actually 2 decimal points precision, so it actually works out better in terms of calibrating and calculations later on. The second chunk of block is the calibration function. I've used a for loop over there to average out at least 1,000 points. I found that 1,000 points were minimum kind of necessary average to be taken out of, because if I did try it with 300 didn't come out to be really good. There was too much drift, and the offset wasn't that good for calibration. So I've actually got a few in here. You can see a few serial prints being shown over here. They're pretty much for debugging processes as well. After that, I've got my cal-A, which is pretty much doing the average of the getting an average value for from all that 1,000 points. And then I've got my PA and ID control variables: error, integral, derivative, error, previous, and output all equals to 0. Thereafter, I've got all my motor pin variables set up. Then after that, I've defined my constant speed and maximum speed. Constant speed, you could also call that as a minimum speed for the motor. I just called it constant speed because when nothing is happening, the constant speed of the motor is pretty much 64, and the maximum is 128. Then my main function starts in here. It's a voice setup. I've got my baud rate 9600. This is pretty much just initializing the whole the gyroscope. And then there's a test connection over here, just to verify the connection of the gyro to the board. Over here I've gone and chosen 0, which gives me a precision of 250 plus and minus. If I needed more, I would actually go to 1, 2, and 3, and I have to build up my code according to it. Then again, I've over here got is a 3 seconds delay. That was because whenever I was testing my PIDs, I had to have some delay in order to take the USB cable out before the whole thing started running. And then I've got my calibration gyro function over here, which calibrates the gyro itself. There's only one calibration in the whole system, so it does it at one point, and then that's it. Then comes the loop command, loop function, pretty much. So the loop body over here. At start, I've got my start time being recorded in milliseconds, and then I'll start doing a bit of a read gyro, so which gives me my raw X values that, as first in the read gyro command we have seen that was giving out, and I'm just taking out the bias, or call the offset, out of the X value and getting a calibrated X value, which I then am converting it into angular velocity. So 131 is, if you read into the spec sheet of a gyroscope, MPU 6050, you'll see that the least significant bits by 1/131 will actually give you the angular velocity in degrees. After that, I've got my differential time, which I will need later on for my other stuff. And I actually take my differential time and convert it into seconds. I've actually casted my dt over here as float, even though I'm actually dividing it by 0.0. The reason behind that is sometimes dividing by 0.0 may not work, and if I cast it, it's pretty much like a double safety confirmation that TS will end up with the decimal points, and then I'm doing giving my ending time is equal to my start time. After that, I'm calculating my position. I have only written posi in that because if I write position, it is actually an inbuilt function or a code for Arduino software. So as you can see, the posi is equal to posi plus the time difference in seconds multiplied by the angular velocity, which will give me my angular position. Now comes the PIE control system. I've got my error worked out over here, the integral worked out over here, the derivative worked out over here, and then comes the output where the constant come in and actually do their magic. After that, I've just got my error previous is equal to error, which will keep on looping, and then on next loop the area previous will be this current error and then the new error, and that's how it works for the derivative. So that's fine. I've got a few more debugging values over here. If you don't need it, you can just go in onto the top and take the defining display out, and then this nothing will show up. After that, I've got a code for maintaining the pulsation width module of the motors. I've just gone and actually subtracted the output from one and added the output to the other, which will give me two different values, and later on I'll explain how it rotates according to it. So after that, I've got is restraining output to motors between maximum and minimum as defined, or maximum and constant as defined. So this is pretty much just doing is checking whether the speed is actually in ballpark of 128 to 128 and 64, the minimum being 64 and the maximum being 128. So this is pretty much just checking that. Probably could have used actually any other function and made it a lot smaller and easier, but I just thought if was the most simplest function I could actually use over here. And then again, there's few debugging debugging codes over here. So as I said before, I had two LED lights hooked up to the board. So one LED light would turn when one motor was actually countering the spin of the board, and the other would turn countering the spin anti spin of the board. So it's pretty simple in here. I'll just use the if else command. Then I've got the code for my test A in here. It's pretty much just doing is checking the current time to be more than 10 seconds, and well, not 10 seconds because I've got 20 seconds in here. The reason behind that is that my calibration being out of 1,000 points, it actually takes quite a while, 15 to 17 seconds, around 15 to 17 seconds. And then after that, I've got my set point is assigned 90, and then that's why you will later on see that on test 2 or test 1 that after 20 seconds of the motor being started, the board will spin 90 degrees, and then again in another 10 seconds, because this is TI, the time interval is only 10 seconds, will the board spin back to its original position is 0 degrees. I think the assignment said minus 90 degrees. I thought minus 90 degrees was pretty much subtracting minus 90. I mean 90 out of the current set point, so that would give me 0 degrees. So this is the test B of the code. And test B is pretty simple. All it does is actually after 30 seconds of the initial start of the motor, where the set point changes to 90 degree and it moves into 90 degree angle and stays there after that, as you will see in the test videos. After that, I've pretty much got is my pin mode set up for my motors, the direction, pulsation module for A, and then brake, and then the same for the B as well. And I've gone and actually written my brakes to be low. That means I'm turning the brakes off, and here is the actual thing is I'm turning motor A in one direction and motor B in the other. And as we had actually worked out the outputs for A and B at top over here with the help of the PID control system, these are put in at this stage over here. So there you go. This is pretty much the control side and the code of the whole Arduino self-aligning code, or you can also call it the Jim's blame signboard programming code. And later on I've got more debugging codes which can be turned off if I just take the defined disp out of the code. So that's it, and thank you. While I'm here, actually what I'll do is I'll just quickly hook up my Arduino and then give it a run and just show you how this works. For the moment I'll go and take my test A and B. Yep, they are diffused at the moment, and I'll also show you how the LED bulbs are working. So now I'm just going to quickly hook up my USB cable into my board. USB cable into my board, and I'm just going to put the 9-volt power battery as well into the Arduino system. You'll actually see that it will start running as soon as I'll hook that up, because it's already got a code in there, so whenever it actually sees power in it, it starts running itself. And then I will quickly compile it, just do a quick check. So as you can see on the right hand corner, it was doing compiling, and then I will upload it. So you'll see that it is uploading now, and I'll turn the serial monitor on my left hand side. So as you can see, it is running through 1000 gyro values for finding the average out of it. And I'll quickly check you down here, and you'll see the green light over there. That's showing that the Arduino is actually running. And there you go. So the Arduino is running, and it's giving me all sorts of output that I had in my debugging codes. So at the moment, as you can see, the motor B is trying its best, because you see the LED B is actually lighted up and not A. And if I just have to actually okay, there you go. Sorry, I'll just have to quickly see what position this is in at the moment. So okay, so that was in positive before. Now if I go and turn it this way, you'll see that turns out up. That's because it's trying to, the bottom motor is trying to counterspin the board motion, and if I come this way, then the top motor starts counterspinning again. I'll quickly take this cable out, and I'll show you that it's working. So, as you can see now, it's going to actually stabilize itself, and if I push it on the negative side, it'll come back again, and you'll see the LED lights actually working. So there you go, and then come back to its primal position, and then you can see that stabilization is pretty good. If I go to the positive, you'll see the same effect again. It'll just come back to its first position. Alright, as you can see, this is a success, 10 out of 10 for me, and that concludes my assignment. Thank you.